It's a cold, wintry, very appropriate for Purdue Friday. So thank you for coming. This must be the hardcore folks. So welcome everyone, and good morning to you. I'm Deba Datta, the Provost, Chief Academic and Chief Diversity Officer. So it is my great pleasure to welcome all of you for the first edition of the New Horizons program that we launched last year, we announced last year. And we are ready to have you meet the winners of the first round. We hope to make this an annual competition. And so very briefly, the Provost Office, as you know, is always looking for ways to support junior faculty, and that's very appropriate. We have several programs for junior faculty to get them started on their teaching, research, and everything else. But it is equally important, in my opinion, to find ways to support our senior faculty, well-established faculty, and this New Horizons program is focused on that. How can we support our senior, well-established faculty? Now here, it actually gives us a new opportunity. The senior faculty already are experts. They get their own funding. They have mastered all that. So what we decided to do after consultations with several folks on campus, find a way to get senior faculty to think about, it's not just the next new project, next new research idea that they have, but get them to think about how can Purdue be known more than what it is today as the progenitor of new areas, new disciplines, new lines of inquiry. So it is an opportunity for senior faculty across the campus, science, engineering, arts, humanities, the professional schools, to come together with the objective of creating something which over time, 8 to 10 years, might lead to an established new discipline, which forever will be recognized that it started at Purdue, or Purdue had a lot to do with the start. So that's essentially what it is. Seeing the contours on the horizon before others can is what New Horizons is all about. So I'll let Vice Provost Hollenbeck give you more details about the competition. But let me just say that the program that you will hear about this morning is not only a brilliant new idea in the scientific realm, but it is something that is rooted very deeply in the local concerns. It is about lack of space. So we all feel this. We are fighting over space, and what you'll hear about is a really new way of thinking about more space for research, habitation, and everything else that goes with it. So with that, let me invite Peter Hollenbeck to give you more details about the program and how we got it started. Peter?
Thank you, Deba, and thank you all for coming on this great chilly morning, the weather of my people. Before we hear about this marvelous project, let me say a few words about the process. As Deba said, this is an opportunity to let Purdue senior faculty really think big. And my role is to serve essentially as an NSF program officer, to hear the ideas coming in and try to identify whether they square with this program's goals, which are kind of transcendental, or whether perhaps they represent, a good disciplinary idea that doesn't rise to this level. So we received a large number of letters of intent, and we worked with the writers to make that decision. And then we encouraged 5 groups to prepare full proposals and sort of work with them along the way. And that's the way the process will play out again in the next year. We then enlisted senior faculty who were very accomplished in the research sphere and had the appropriate expertise to study the proposals, to review them, but not in the way maybe you typically review a scientific proposal in your discipline, but to ask the questions, could this develop into a program that would establish a new field and make Purdue preeminent in it? And we identified one, extraterrestrial habitat engineering. How cool is that, honestly? It's both exciting and innovative, and it's a marvelous fit, I think, with Purdue's historical, broad, deep impact on space science and engineering, exemplified by our rather hallowed roster of alumni astronauts whose portraits are in a hallway upstairs here. And of course, exemplified by the place where we're standing, the Neil Armstrong Hall of Engineering. And I have to tell you, I was in kindergarten for the first orbital flight. I was still a schoolboy when the namesake of this building walked on the moon. So it's burned into the DNA of my generation that this was the most extraordinary national effort, certainly of my lifetime. And just to stand here under this thing here, for me, is an enormous thrill, and also a thrill to introduce you to this project. So, unfortunately, I don't think we can stand here for this purpose and in this space without me making a couple of sorrowful nods to events. Not 2 weeks ago, we lost Eugene Cernan, class of '56 at Purdue. The last man to walk on the moon, or as he preferred to put it, the most recent man to walk on the moon. Gene was a skilled and valiant astronaut. He was many other things besides, including a loyal friend and guiding light for Purdue. Second, particularly someone my age can't stand here and let this week pass without noting that we sadly mark the 50th anniversary of the tragic Apollo 1 fire, a ground accident that killed 3 astronauts. Seen here, Roger Chaffee, Ed White, and Gus Grissom. Chaffee and Grissom were also Boilermakers. They were our own. But this isn't a memorial service. This is a celebration of the future, and this university and its space research have always looked boldly and optimistically into the future. So in case you haven't heard, get this. In this next year, the 2018 mission will find not 1 but 2 Purdue alumni simultaneously on the International Space Station. And that would be, I don't have an effective pointer here, but Drew Feustel, who's in the upper right here, and Scott Tingle, bottom right. 2 Boilermakers on the space station, and the lead flight controller on the ground will be Gary Horlocker, another Boilermaker who is not pictured. So in total, we're taking it over. But back to cases. We're here to kick off an innovative, collaborative, interdisciplinary research plan, the first fruits of the New Horizons program. And the investigators you're going to hear from today plan to design habitats for human beings off of planet Earth. So I'll just say it one more time. How cool is that? The principal investigators for the project who are with us today are Antonio Bobbitt, Shirley Dyke, Jay Malash, and Julio Ramirez. And please join me in welcoming them to the podium.
Okay, so good morning. Thank you for coming. We are thankful that you are sharing with us your excitement about this new program. And here we want to really thank Provost Dutta and the university for really supporting this idea that started very slowly with a small group of people thinking about what comes next, what exciting opportunities we might have, and building, as we'll show you in a minute, building on some of the work that we have done. So this is us, and this is the title that we started with our proposal. And I want to introduce the PIs of this proposal. Myself, Antonio Bobbitt. I'm a professor of civil engineer. I'm geomechanics by education and by training. Professor Shirley Dyke. She's a professor in civil and mechanical engineering, structural and hybrid simulation. Professor Jay Melosh, Earth, Atmospheric and Planetary Sciences, distinguished professor, and his area of expertise is planetary science, and particularly something that I always find very cool, which is meteorite impacts and how craters are formed and seismicity associated with that, which will be handy as we move forward. And Professor Julio Ramirez, also professor of civil engineering. His specialty is in structures. Also, he's the director of the Network Coordination Office, funded by NSF. This is the next NIST. This is NERI, and we are both co-PIs on this project. And so there is a little bit of synergy here, and you begin to see a little bit where we are going with this. There is a combination of planetary science, a combination of engineering, there is a geomechanics component, there is a structures component, and that's a little bit where we are going with this. So why we're here? We're here because this is the unending quest of humanity. We are explorers. We try to seek new knowledge, new opportunities. We want to go places where there's been a challenge. And this challenge is because there is something to gain. That would be maybe some economic issues. There might be some opportunities for development. And humanity has been moving forward most of the times in a continuous manner, but thanks to very few individuals, sometimes we've been doing big jumps, people that have shown us the way and have changed things forever. And here I offer some of the examples, starting with Christopher Columbus, who, seeking new paths to reach China, found the shores of the Americas and changed the world forever. There are many others. Magellan in the early 1500s showed that, really proved that the world was round and found new ways of finding new paths for navigation. Or, for example, Amundsen, who overcame the challenge of going to the North Pole in conditions that were extremely difficult. And our own Amelia Earhart in 1932, which crossed the Atlantic solo. Many others, like Edmund Hillary, who climbed the Everest, a great challenge, the highest point on Earth. So these are people that show that things could be done, and how could be done. And why? Because that was the challenge. And of course, John Glenn, the first American who went around the Earth, and Neil Armstrong, the first human who set foot on the moon. And this is where we are, right? This is the Armstrong Building that honors someone like Neil Armstrong. And we couldn't pass the opportunity to show you the great, exciting moment in 1961 when this thing happened.
It's one small step for man, one giant leap for mankind.
And now comes the scientist, the person who is curious about this new environment.
Surface is fine and powdery. I can pick it up loosely with my toe. It does adhere in fine layers, like powdered charcoal, to the sole and sides of my boot. I only go in a fraction of an inch, maybe an eighth of an inch, but I can see the footprints of my boots and the treads in the fine sandy particles.
And for someone,
Houston, we're copying.
For someone who is like me at geomechanics, this is a tribute to someone to the science that you go there and you observe something that nobody has observed before, a new world that was just right there and exploring and being the wonder of this new discovery. And this is our sun. this is where we are. This is our home. And if you look at it, there is these great opportunities for exploration, these great opportunities for discovery, to find new answers to all questions, such that what is the origin of the universe? What new resources we're going to find out there? There is a talk, right? Steve Hawking said that if in the next few hundred years or in the next 1,000 years humanity has not been able to move outside of Earth, we are going to disappear, because the probabilities that something goes wrong, they accumulate over time. So this is where we're going. It's not that we are going to do something that is completely out of thinking or impossible. That's something that we need to have, and that's something that we will to have as humanity, because we have the drive to explore, because we have questions to answer, we have things to gain, and this is where we are. This is our home. And as I said, there is plenty of opportunities, and that's where I think that our research and our proposal fits very nicely. That's not an impossible task. We've been there. We've been to the moon. We've been to the moon several times. We can look at the moon maybe not as a place to obtain resources, but maybe as a staging place for new adventures and new endeavors, and probably to go out and explore other worlds beyond our solar system. However, the conditions on the moon are very difficult. Here you see two pictures, one taken from Apollo 11, the first mission, the other one from the last mission, Apollo 17. And if you look at the surface of the moon, this is a very inhospitable place. There is no air, there is no resources, there is radiation, and the question is, what can we do to have a permanent settlement, because this is something that humanity will do. And it's going to be us here at Purdue who are going to start doing this. And of course, the next challenge now is Mars. We have been there already, okay? It's further, it's more difficult, but we've been there. So we are on the shoulders of giants. We are building on the work that other people have done. The only thing that we need to do is go a step further. And I want to share with you also, the pictures that have been taken from the surface of Mars. It has a kind of an Earth-like appearance, a little bit different than the moon. But again, it's a very harsh environment, very little atmosphere, very little air, mostly CO2. It's a barren place. There is radiation that is going to make things difficult. So where is the next step? What lies ahead? What lies ahead is our vision. It's our vision to have permanent human settlements on the moon and Mars and other places. However, if you look at what proposals lie out there about what can be done, and this is just many of them. If you go from a scientific or an engineering point of view and just check a little bit, is this feasible? Is this possible? The answer immediately is no. These, unless we are able to develop new concepts, new materials, new technologies, our construction or a structure like this is not going to be able to sustain human life. One, because it's not going to be able to sustain radiation. We cannot use the materials on the surface because they are radioactive themselves. They've been exposed to solar radiation for millennia, cannot be used. Also, these structures are not resilient. Any problem that these structures may have are going to end tragically the settlement. In addition, we have load conditions, right? We engineers, that we are beginning to look at those. They are going to have load conditions that are not found here on Earth. And one of them is meteorite impact. Meteorite impact that can be a direct impact, or it could be an impact nearby that is going to produce seismic waves that may be large enough to damage the structure. And these structures are not resilient. Also, we need to think in ways that have to be sustainable. So what we really need is to find the new science and engineering that is needed to make these settlements possible. So The rest of the presentation, what we're going to do is look ahead and try to begin to explore what are the grand challenges that are out there that we are going to start tackling with this proposal. This is a great opportunity for us. This is a great opportunity for Purdue. We're going to be looking at the opportunities and our plan and how we can get involved. And Professor Shirley Dyke is the one that is going to talk about those. But if we look at how such a big problem can be tackled, there are three ways that can be done. One is the concept of the biosphere, where organisms and their habitat, meaning us, we can be fully isolated from the environment. The other way of thinking about this is terraforming. That says, well, what we're going to do is adapt the media, these harsh environments. We're going to adapt to our needs. We adapt the medium to the needs of the organisms. And the third one would be genetic engineering. What we're going to do is adapt the organisms to the harsh environment where we are going to put them. The way that we're going to approach this is by looking at the concept of the biosphere. And this is an example a little bit here on Earth of Biosphere 2. This is being built in Arizona. And it's a way of exploring on how an ecosystem and humans can live together in a closed environment that is going to be sustainable. We have learned a lot about those, but of course, one of the advantages of having a biosphere here on Earth is that there is a problem, you open the door and you are on a benign environment. That certainly is not the way that is going to be happening on the Moon and Mars, where certainly you're going to be millions of miles, days, months away from the safety of Earth. And so this concept of saying there is a problem, we can get away from it, that's not possible. So we need to think of ways that these settlements are going to be resilient and they're going to be sustainable. So we look at what we've learned about the exploration on the Moon and Mars is that on the left, what you have is a picture of the Moon. On the right, you have a picture of Mars, is that we have no resources. There is very little or no air. There is plenty of cosmic radiation. Water is not as ubiquitous as we have here on Earth, so that's something that we need to look at. The loading conditions are going to be very different, and that's something that we need to start thinking and learning about how we are going to be dealing with extreme events that are not thought here on Earth, and particularly meteorite impacts. We have an atmosphere that protects us from those, but this is not the case on the Moon and Mars. And if you look at, the question is how prevalent are meteorite impacts? Here on Earth, it may not be that prevalent, but on the Moon, on Mars, they are. And if you look at the landing site of the first Apollo, the site has changed significantly because of the meteorite impact. So they do happen, and we need to think about on ways that we can design to be safe. So how this idea ended up. It's like everything. It ended up by doing work that may or may not be related to what we do. And this started with the work that Professor Melosh, Jay Melosh, and others with Aero, and from Earth Atmospheric Sciences, they did looking at the density on the Moon, on the surface of the Moon, through the GRAIL program. And this picture that you see on the bottom right with these blues and light colors provides a measure of the density of the Moon, of the surface of the Moon. And the lighter colors, what they are giving us is areas where there is changes in density. We find that the density is much smaller. And the hypothesis behind that is this is due of lava tubes, empty lava tubes, below the surface of the Moon that were created when there was volcanic activity on the Moon. They stopped, and these lava tubes became empty. And the picture that you have on the top left, this kind of opening, this is a skylight. This is a hole on top of one of these lava tubes that may be produced because the lava itself, the rock, may have been a little bit more fractured, may not have been good enough, or because maybe there was a meteorite impact that provides the collapse of this cavity. The picture that you see below is a larger scale picture, and the center you see this cavity. So I got involved in this doing this research, because the question was, well, we see these lava tubes that have a size that is orders of magnitude larger than the size of the lava tubes that we see on Earth. So the picture that you see on the left is an actual lava tube on Earth, and the size is for the order of, I don't know, tens of feet maybe, and you see for scale a person. The picture that you see on the right on the top with these contours, which are stress contours, is how a lava tube, looking at these density differences, these density singularities, might look like. We are looking at hundreds or thousands of feet in size, and on the bottom left, what you see is the city of Philadelphia. Fitting in one of these lava tubes. And the city of Philadelphia is because the student working on that, that's where he grew up. But it provides a sense of what is the differences and the size of what we are talking about. And I was involved because the question was, how realistic is that from a geomechanics point of view, that these are stable? So we did our simulations, and what it seems that under the right conditions, we could have these large lava tubes on the moon and also on Mars. So you look at that, this would be a nice way of sheltering astronauts that are going to be visiting the moon and Mars right away, because they would be protected from radiation. We would have a cover instantly, protected from meteorite impacts, protected from the harsh environment. They could be pressurized maybe, so we could have an ecosystem inside that would provide right away a site, a place for extraterrestrial habitats. What you see at the bottom is a little of a rendering of how one of these lava tubes of the size of Earth would look like, just a concept. But of course, there are two concepts. One is the settlement on the surface, like you see on the top picture, where you have different modules that can be brought there and put them together. That would require a lot of materials, a lot of travel from the Earth there, placing all these modules. It would require also how you create these foundations, earth movements, so on and so forth. And at the bottom, you see this concept of taking advantage of what nature is already giving us. And it looks like kind of going back to the beginning of humankind, right? We started in the caves, and as the technology developed, we were able to go out and then explore and develop. Maybe we need to think about taking advantage of the same concept. So this is where we come. This is what we want to look at. This is extraterrestrial habitat engineering. And of course, the challenges are many. We think we know some of it. There are many things that we don't know, and these are the research questions that we need to develop through this program. And that's where we want Purdue to be the leader. So there are challenges regarding the resources that are needed for these permanent habitats, regarding air and water and energy and food. There are challenges regarding to the structure itself, how we are going to create these buildings, new techniques that to build and move large volumes of earth around. Maybe we need to develop some thinking of robotic ways of doing this, of transportation. Challenges regarding safety, not only the health of the astronauts, because they're going to be exposed to radiation, they're going to be exposed to very long times of low gravity, but also protection from extreme events like meteorite impacts, and also resilience. The structures, we know that the structures, the buildings, are going to have problems over a long period of time. So how can we design them such that they can recover quickly and survive these extreme events? And that's a very important question that here on Earth is important, but certainly is a challenge, and it has a larger importance out there. And also human prosperity. We are going to have a number, maybe low number, very large number of people There is a plan now from Elon Musk that says in the next 40 or 60 years, we are going to bring 1 million people to Mars. Okay, so what society, what interactions are going to have with a permanent settlement such that human settlement can thrive, that they can have privacy, and they can have human interactions such that the colony is going to prosper. But the issue is that currently, all this science, all this engineering, all this technology that is needed to accomplish these grand tasks are not available. And that's what we want to do. We want to start, we want Purdue to be the leader, to start on this fantastic, cool idea, as Peter was mentioning. So there is an opportunity for developing new materials that may be needed to resist extreme events, large loads, radiation, opportunities for construction, maybe looking at robotic construction, opportunities to develop new sources of energy. Solar energy certainly is a possibility, but maybe we need to look at others. For example, nuclear energy might be an issue. Transportation, how we're going to be moving people, personnel, and a large amount of goods within these settlements, between different settlements, from settlements on Earth, and certainly all these resources that are needed for human thriving, food that have to be self-sustained, all the resources of water that is needed for that. And of course, we have the experience from all the programs that have been developed by NASA, that all the technologies that have been developed, they have found a direct application to our lives here on Earth. So we expect that all these discoveries, all these advancements that we're going to be able to put forward, they are going to have a direct benefit also here on Earth. And now I'd like to invite Professor Dyke to talk about what are the opportunities that are going to come from this task, and also our plans to move forward and our plans to get Purdue involved.
Okay, so over the next 2 years, these grand challenges give us a lot of opportunities. We've identified the grand challenges. So let's talk about the opportunities and then how some of us can get involved, so the Purdue community can get involved in this. So extraterrestrial habitat engineering is our vision. But again, the opportunities rely in the science and technology. How do we actually develop the know-how? How do we do the 3D printing of these habitats, building these habitats, protecting these habitats? How are we going to answer the research questions that will make those things possible? We have new resources. We have to identify those resources, figure out how to mine them, figure out how to use them effectively, energy and such, so that we can actually build these habitats. Of course, then there's going to be technology transfer. So every item that we're talking about here is probably going to transfer into some companies that eventually are going to be building these, that are going to be developing these settlements, and maybe a real estate agent for Mars, I don't know. And then those technologies are also going to come back to the United States, or back to the planet Earth, I should say. So everything is going to go in both directions. It's going to go into the companies, into the planetary habitats, and then it's going to come back for us. There's also a strong need to integrate the learning and teaching activities that we do here with these activities. When the students are going to go into these companies, they have to be prepared for this strongly interdisciplinary field. And thus, the people who are doing this now are doing this with a very different type of background, but we hope that as a new academic discipline, this will allow us to teach people to prepare for this type of environment in a different way. And then, this is an opportunity for Purdue to establish a leadership role in a particular area, an exciting new discipline where students, faculty, staff, everyone at this university could get involved in this program, is the way that we see it. In fact, there are already startup companies that are doing this type of thing, right? There's companies you've probably heard in the news. There are companies that are actually mining, or that are talking about mining asteroids, trying to develop the technologies, to develop the know-how to make that a possibility in the near future, so that we can bring those resources back here, so that we can use them on other planets or on the moon for habitats. And we want to generate the students that are going to go out and work for those companies. That's an immediate goal, and then there's going to be new industries involved in that as well. How do you get involved? How do we get involved? All of the people at the Purdue community. That's what we really want to do, is to engage a very broad cross-section of the Purdue community in this activity. There's many disciplines that are very obvious. There's probably also a lot that are not so obvious. We may see ourselves here, and there's lots of things that are probably not going to be visible. We see engineering, we see the Polytechnic, we see the College of Science, we see agriculture, as well as health and human sciences. Right? So we need to engage all of these groups to make this a success. It's not going to be successful if we just deal with the physical needs. We have to also deal with the behavioral understanding of how do people thrive in this type of environment? How do we answer those questions? So we've decided to ground our activities in 3 thrust areas. One of them is building knowledge. Building knowledge is referring to the research questions that we need to address, we need to understand, we need to work toward a solution for, so that we can develop these habitats. The second area, the second thrust area that we have is concept design. Concept design is the conceptual as well as the physical manifestation of how those settlements might be realized. We intend to build several concepts, work with people across Purdue, and develop those concepts, and then criticize them and try to determine what's wrong and what's really going to work and what may not work. And then we also need to build partnerships. This means partnerships with organizations like NASA and the European Space Commission, and as well as organizations around the world. It also means building partnerships here within Purdue, building partnerships with other institutions to try and make this a strong program for Purdue. So the activities that we see happening over the next 2 years on campus, first of all, is a seminar series. Beginning later this semester, we will be inviting speakers to campus, and the objective of that is for us to explore what's already been done and for us to understand what needs to be done still, to figure out what those research questions are, to refine those, and discuss with the Purdue community what those need to be, what we need to do. We also have plans for programmatic and curricular directions. The objective of this, or one of the objectives of this, is going to be, at the end of the 2 years, to have a path to a minor that involves broad participation across campus. Many of the different departments that would be needed in order to make this a realistic discipline, an academic discipline. As a part of this, we also have design competitions. So in order to develop these concepts, realize these concepts, build these concepts, we would like to engage design classes, capstone courses, EPICS program, and anyone else who sees a way in which we can work together to try and integrate this into the curriculum that we have right now as we learn about developing that new program. Concept design is going to be in those classrooms, but it's also going to be in the laboratory. It has to be an interdisciplinary. We have to be thinking about how do we support the life, how do we support those individuals that are going to be living in these habitats, but also how do we build these systems. We're going to be considering both above ground as well as underground habitats. Both seem feasible in some ways, and we would like to explore both and look at the pros and cons and understand that. And we do expect to have significant student involvement, and we actually have a posting already up for the SURF program. If people are here and they're interested, there's an announcement for an undergraduate, a couple of undergraduate opportunities this summer. Early in year 2, we're going to have an international workshop. So that's probably May-ish or so of next year. And we will be inviting thought leaders. We will be talking about the research questions, discussing what needs to be done, basing that on what we've already learned at that point. And we hope to engage as many people as possible from the Purdue community to come and participate in that workshop and think about, what we could be doing. Are there research needs? Are there educational needs that we can launch after or during that workshop? And we're also going to be exploring a center to involve people on campus as well as off campus. So we're going to be handing out a flyer during the Q&A session. And this is our email, reth@purdue.edu. We also have a YouTube channel, although there's nothing posted yet, but we do have a YouTube channel, and we're working on a website. So please be looking for this information. If you'd like to join the announcement list, just send us an email and ask to join the announcement list. We haven't formally set up the announcement list yet, but we will be doing that. We're also going to have a town hall meeting February 24th, and this will be written down on the piece of paper that you get. February 24th at 2:30 in the afternoon over in Potter. Everybody's welcome to come. We'll probably have some cookies that afternoon, and we'd like to get you engaged. So it was nice to see that after we came up with this presentation yesterday, we also received a quote from William Gerstermeyer, and he's at NASA. He's the Associate Administrator for the Human Exploration and Operations Missions Directorate at NASA. And his quote was very encouraging for us. It reads, "The challenge to create habitats that will protect future explorers in extreme environments in space creates opportunities for groundbreaking innovation. Developing the capabilities to permanently expand human presence in the solar system is a global effort requiring the integration of many different disciplines and contributions from the best and brightest in academia, as well as the fellow space agencies and private industry to make this vision a reality." So we really appreciate the support that he's shown for the program and the ideas that we have developed. So together, we hope to work with the Purdue community to build safe, comfortable, and resilient habitats on the moon or Mars. And hopefully, this is a vision that we can realize, and we'll be working toward developing this as an academic discipline to support that goal. If you'd like to get involved, again, there's a copy of the email, and we will be distributing a flyer that has that information. Thank you very much.
We have a question. We have a question right here, please.
Hi, very nice presentation. Thank you. When I first heard about this, I guess I was limited in my thinking that we were talking about human colonization, but as I saw some of your slides, I realized perhaps we could also be talking about robotic colonization when we were looking at the mining and that sort of thing. Will that be part of your scope, perhaps, to also look at providing habitats for a robot army for such as a mining operation? Thank you.
Sure. No, go ahead.
Okay, so initially the focus was on human habitats, and we were looking at this as support to what humans may need out of space, and certainly robotic tools seemed. Initially, that seems a way to go, particularly because you're going to go on the surface, you're going to be mining, you're going to look for resources. The environment and the exposure to radiation, that's certainly something that prevents long stays and maybe the protection that the astronauts need. So that seems like a good support. But again, that doesn't preclude that going in this direction doesn't open opportunities for others. So initially our thrust at this point, and things as we evolve may change, was on human settlements and then explore what is needed to support and sustain the human settlement on the planet. Jay?
Maybe I could add that one of the things we've learned from the ISS, in fact, one of the reasons for ISS was to understand how humans could explore space. One of the things we've learned is that we really need a partnership between humans and robots. As you may know, astronauts do not like EVAs on the space station. It takes too long to get in and out of spacesuits. We now have Robonaut 3, which is taking over some of those tasks and allowing the humans to be more comfortable and in more of a guidance role while the robotic element does some different tasks that it's more specialized to. I see mining as probably something that involves that. It's very hard to do to allow a robot to do autonomous mining with all of the various things that will happen and have to have decisions made. And so what I think we really need to look at is the joint exploration of space with humans and robots together.
If I may add, what your question is bringing up something that is very popular in the world today with regards to natural hazards, which is performance-based design. What that means is that you are not thinking of a unique type of habitat. Each habitat will have its own challenges and performance requirements. So when we think in terms of extraterrestrial habitats, can you imagine that breadth increasing with regards to the potential? So it's part of the grand challenges. What are those performance requirements for what types of missions or operations?
Other questions?
So thank you very much for a wonderful presentation. Enjoyed it much. And on this one, you might not have thought deeply, and that is fine. But have you considered the behavioral science aspect of this? And I noted you had one slide, but that might be good to explore and engage from the get-go.
I believe that you mean the human behavior, understanding human behavior and how they would react to this sort of environment. Yeah, we've actually talked about it quite a bit and tried to understand exactly which ways we need to go, how many, what other individuals will need to get involved. And we have to involve people here at Purdue and perhaps elsewhere that study this. And it's not an easy problem to study because you can't do experiments for years, I suppose, to try and understand how humans on the Earth, to understand how humans will respond to being many years separated in an environment that's enclosed. But it certainly has to be something that we incorporate, and we want to work with the right people to make that happen. So,
if I may add, one of the things we've learned, and I'm not a social scientist, obviously, is that humans need to be entertained. Monotony is disastrous for being efficient, for thriving. And so, for instance, we're thinking in terms of what role could virtual reality play in this whole operation, and what disciplines should be involved in addressing that very important aspect, which is how do we keep the humans more or less happy in that environment.
Any other questions?
Hi, thank you for such an amazing presentation. Being a geotechnical student, I would just like to inquire, like whenever we think of anything starting, so you think basically then how's the environment there, the air, the water, the ground. So when we talk about the ground, so is like investigating the ground on the moon and the Mars as a part of the project, and how are you going to do that if it is?
We have some information already about what we expect about the behavior, granular soils, low gravity. Then, of course, we see the features that we see on the surface, and we compare those with the features that we see on Earth, so we can extrapolate about the processes, the geologic processes that have produced these features. And on that, we also have an idea of what would be the expected behavior and properties of the materials, not only on the surface, but underground to some extent. Okay. So of course there is an opportunity of looking at the data that is out there already, and maybe Jay can add to that. But also with the data that are there, mechanics, we believe that the mechanics is mechanics, so we can use these tools that we have learned on Earth with caveats, of course, because gravity is going to be different. The interaction between different gases and different fluids that we have here on Earth is not going to be the one that we have on Mars, because the atmosphere is going to be completely different. So how things behave, how the loadings, all this is going to be a challenge. I'm not saying that we are going to be able to solve the problem. The issue is what are the research questions that we need to put forward such that we can do research on that and learn on things that are really needed for this. So we are not thinking of saying, on the end of this program, 2 years or 5 years, we are going to be ready to say, hey, this is what needs to be done. But I think that we're going to be ready to take the lead and say, these are the research questions, these are the issues that we need to be looking at to answer this fundamental question that has come out after all the work that we have done. But we have the tools. Okay, so for example, on the analysis that we did of these caverns on the moon, we used the tools that we are using here with some caveats and judgment about how these tools might be or not fully applicable to the conditions on the moon where the gravity is going to be different. But that provides you an assessment that you know what are the limitations, and at the end you know what is the risk and uncertainties associated with that.
I could add to that. We are ourselves and partnering with others in trying to understand the subsurface environment on the moon and Mars. You may know that a number of missions, including the Chinese Chang'e 3 mission, had ground-penetrating radar aboard. The Japanese Kagoya mission had a ground-penetrating radar. We're actually partnering with them in a piece of research we're about to publish, that they have detected some of the lava tubes that we were illustrating here that we found with GRAIL. We also have a proposal to go back to the moon with a ground-penetrating radar and detail the subsurface environment there, looking for the exact dimensions of these lava tubes. We first detected them with gravity, which does not, in fact, tell us how deep they are, doesn't tell us the details about the caverns. We need different techniques, and we're planning to do that with ground-penetrating radar. I might mention that the Mars 2020 spacecraft will itself have a ground-penetrating radar aboard, so that we, as well as other people, are very well aware that the subsurface is an important aspect, and we're planning to probe that in the future.
Thank you.
Maybe I'll add one more thing, which is that we do hope to explore some advanced simulation techniques, which one of them is called hybrid simulation, which allows us to study the way that the structures behave in an environment not on the Earth. So we can simulate conditions that are beyond the Earth's gravitational pull and other types of soils that we might not have here. And we have the ability to do physical testing of settlements, structures, with different conditions using hybrid simulation. So.
Hi there. As you guys start to think about the different research questions that will come up in this discipline, and you start to realize maybe that some of these questions don't have the data to be answered, will you start to seek out to development of instrumentation or different missions to kind of get that data? Will you plan how we can, take the first steps to actually creating a habitat?
Yeah, one of the big goals of this is to write our own proposals and encourage other people here at Purdue to work with us or to write their own proposals to seek out the answers to those questions. So within the scope of this 2-year project, we're probably not going to be launching any missions, but we do hope to be working with people to encourage that to happen, new missions to be pursued.
Yeah, I should say, even the smaller missions with NASA take a number of years preparation, and within the 2-year time frame that we have here, we probably will certainly not be able to go from mission concept to completion of a mission. But what I hope will come out of this project is the ideas and perhaps the proposals that will go forward that within another 3 to 5 years will result actually in a spacecraft mission that will do exactly what you suggest. Of once we know what information we need, we can develop the instruments to gather that and actually go on with a mission proposal to start building the instruments and flying them.
Any other questions for the investigators? If not, I think you're all free to boldly go, or no one has gone before. Thanks so much for coming.